Okay, we're doing Giancoli 333. It's kind of an abstract problem about finding the angle, the launch angle at which the range of a projectile will equal its maximum height. So, since we're looking at maximum height here, what I'm doing is stopping my thing there. But it's important to know that that's not the range, right? This is only half the range. So if I call this delta y d, I'm going to call this delta x for this interval d over 2. Anyway, since we're looking for the highest point, I'm going to try to develop an expression for that highest height d first. So I know at the top the v of y is 0, so I know the v iy, or at least I have an expression for it, and I know my acceleration. So I'm going to use this expression, v of y squared. It's viy squared, which is vi squared sine squared theta, plus 2a delta x. The a is negative g, so I'll get a negative in there, and that delta y we've called d. So this I know goes to 0, so my d, my maximum height, is vi squared sine squared theta over 2 times g. Okay, now this is great, but I don't know the vi. I'm solving for the theta, so that's fine. The g is in there, and that's okay too, because I know that. So since we're talking about relating this to the range, I'm going to look at the range equation. So that delta x for the whole thing, not for the picture I have drawn, but for the whole thing from the launch to the ground. We know that it's level ground, so I can use the range equation, vi squared sine 2 theta over g. Now these are really similar, and we want them to be equal, so I'm going to substitute this in for d, and I can say that vi squared sine squared theta over 2g has to equal vi squared sine 2 theta over g. The g's can cancel, the vi squareds can cancel, so now we're in a shape where we only have theta, and that's good times. So I can say that sine squared theta over 2 has to equal sine 2 theta. And you can, at this point, you can slide one of those over to the other side and use your calculator to solve the equation, which is okay. Or you can use that trig identity that we use to actually derive the range equation. So this is 2 sine theta cosine theta. This is sine squared theta. I can cancel one of the sine thetas, and what I'm going to get, if I try to isolate theta, I divide by the cosine, so I get sine over cosine on the left, or tan theta equals 2. So the inverse tan of 2 will be theta, and if we go to our calculators, we'll get 63 degrees. It's interesting that the g ended up going away here, so this answer would be the same no matter where we are. Oops, just noticed a problem here. I forgot my divided by 2. I lost that, so this needs to be 4. This needs to be a 4. This needs to be 4. Okay, just a little revision there. So the inverse tan of 4 is what we want now, so 76 degrees is actually what we want. Yeah, like I was saying before, the g doesn't matter, so you could do this on the moon and it would be still the same angle. It doesn't matter how fast you fire it. I mean, you do need to have an acceleration, otherwise it wouldn't be a maximum height. But other than that, you're over level ground and you have a vertical acceleration. That's all you need, and this will be true.